There we go.
Okay. Yeah. Well, thanks, Jamie, and thanks, folks, for having me. It's nice to have an opportunity to present some of this work. So my goal is to present this info in a structure that's slightly different from the paper that I have on this. It's hopefully more suited for a synchronous presentation. So that is all the stuff here is in the paper, but I'm going to be framing it slightly differently, and experimenting a little bit with the structure of how I'm presenting it. So getting right to it. Why isn't it not? Okay. So the question then is sort of, why simulations? Probably some of you already know why simulations are important, but I'll say a brief word. They're becoming more and more necessary. In particular, they're often needed where we don't have ready access to, phenomena of interests in, the usual experimental or sort of observational ways. A galaxy, for example, it should go without saying you can't bring it into the laboratory and poke and prod and do all those things that you might want to do with it. And moreover, all the data that we have of galaxies, at least for many of the processes of interest, are basically snapshots because many of the processes of interest take place over sort of billions of years. And so, well, obviously you can take snapshots of different galaxies at different stages of evolution. It's not quite the sort of observational gold mine that you might want of something where you get to observe it throughout its entire sort of, throughout the entire process. And so simulations are one way to try to fill the gap left by these more traditional methods. And, in any case, they're becoming essential tools in many subfields. I'm going to talk a little bit about galaxy simulations here, but they're obviously pretty important for things like large-scale climate modeling, and so it's not just in physics that these are an important problem. And so the question then is why we believe the stuff going on in the computer simulation, on my computer down here, is going to reliably tell me about what's going on up there, out there in the world. And I'm certainly, in the course of this talk, not going to be able to give you an entire story today, but what I'm hoping to do is follow a particularly interesting thread that has come up in the philosophical literature, and try to make some suggestions about where I think the conversation should go from there. But first, some sort of terminological stuff. I'm going to be sort of relying on the jargon of a framework sometimes called the verification and validation framework, which was something that came up, was sort of arose mostly in sort of engineering fields. Interestingly enough, one of the big fields was computational fluid dynamics, which has some obvious theoretical overlap with things like astrophysical dynamics. And so I should stress here that I'm on the one hand pulling the jargon from this system, the terms that are used to refer to the various moving parts of a simulation. But the verification and validation framework is also associated with a set of like prescriptions about how simulation justification should take place. And I'm going to sort of tacitly accept the former and sort of push back against the latter in this. So I just wanted to make sure I distinguished those two things. So some terminology. We have, of course, the target system, which is the system that we are trying to model or understand. In the case of the examples I'll be using in this, it's galaxies, typically galaxy evolution processes. We have the sort of conceptual model on the other, which is what we typically think of when we talking about like a model of a particular phenomenon, which is the equations and the modeling assumptions that we take that to represent our theoretical understanding of and sort of conceptual understanding of the target system. And in the case of simulation, the new ingredient is this computerized model, the thing sort of in the middle, which is the numerical instantiation of that conceptual model on the computer program. And as most of you probably are aware, in order to put the conceptual equations onto the computer, we typically need to discretize them so that they are sort of tractable and solvable by the numerical methods that we want to use. And in particular, I should stress here that we're interested primarily in simulations where the conceptual model is sort of complex enough, the equations of that are complex enough that we can't solve the solutions of these equations analytically. It's precisely in these cases that the computerized model can act as a kind of bridge between the conceptual model on the one hand and the target system on the other. And generally, the goal is to make sure that we have a sort of a correspondence between the two via this bridge of the computerized model. Now, verification and validation, the two sort of central terms in this, are sort of refer to the sort of two components of that bridge, as it were. So verification is generally taken to refer to we say that a simulation is verified just in case its computerized model faithfully approximates the underlying sort of conceptual model, the conceptual equations, typically within some regime of interest. And then on the other hand, we say that the simulation is validated just in case, on the one hand, there's a correspondence between the target system and the output of the simulation. I should flag here that the word validation is often used in different and contradictory ways in this literature. Klaus Weisbart has a paper where he goes into all the different ways that people use this word, and so I'm using it in a very particular way here, and I just wanted to flag that people will often use the word in ways that are inconsistent with what I've mentioned here.
Quick question. So there is no assumption about the relationship of the target system to reality, right? In this scheme.
Oh yeah, the reality and the target system are. I'm taking those to be the same thing.
Oh, they are the same thing. Okay.
Yes.
The target system may not. I mean, can it be a reflection of the reality? Can be mapped onto reality, or it is reality? I mean, that's going to be.
It is reality. Yes.
Reality. Okay.
Yeah, and this,
Kevin, I also have a question here.
Mm-hmm.
What's the difference between faithfully approximate and accurately reflect? The verification, you say faithfully approximate. Validation, you say accurately reflect.
Oh, these are not distinct. Yeah, sorry. They're both referring to sort of representational correspondences, because ultimately the goal is for these two parts of the bridge to be continuous enough that we can infer that there's a overall correspondence on the basis of these two sort of sub-correspondences, if that makes sense.
So I shouldn't think that a verification and validation as two separate things.
Well, they concern different relata. On the one hand, we have the conceptual model, the equations that represent the theoretical understanding, and the simulation code. And on the other hand, we have the simulation code and the real world, as it were.
Okay.
And in particular, like the big thing here to focus on is that this seems to sort of separate out the verification, which is concerned with the numerics, like purely with the numerics, and validation, which is concerned with the physics, on the other hand, that these are two sort of separate things.
Thank you.
And additional questions are fine. I assume this is the practice in this kind of seminar as well. Okay, so the V&V framework is, again, I said, also sort of associated with a particular position on how simulation justification should proceed. And it's generally motivated, these prescriptions are generally motivated by this two-part structure. So the concern is that errors in the first part are going to potentially cancel out errors in the second part if we don't sort of, and leading us to giving us sort of false confidence in the adequacy of our conceptual model, given that there's some errors in the simulation code that are accounted for by our on the validation side. Now, to mitigate this concern, the idea is that we're going to separate out these two procedures, not just sort of conceptually. Obviously, we just did that conceptually, but both also in practice, in sort of justification framework, and they're going to perform sort of separately and serially. Yeah.
What counts as an error?
As an error, so where there's a discrepancy. So a numerical error might be that if there's a pretty significant difference between an intolerable difference between the numerical output of the code and what the true sort of analytics, the true sort of conceptual equation solution would be. That would be an error on the one hand, and on the other hand.
But why would you have that? Because the conceptual model informs the implementation, the numerical implementation.
Yes.
There may not be errors, there may be simplifications or something, right?
Of course, yes. And in fact, that's part of the concern, is that many of the simplifications that we need in order to make these things like computationally tractable are going to create numerical errors that are going to lead to break the correspondence that we're trying to establish. Okay. Okay. Sorry. and yeah, so this is, Eric Winsberg calls this the separability thesis, which he's in particular criticized. So to mitigate this, you know, again, to mitigate this concern, the prescription is to separate out these two components of, and in particular for have them proceed serially. First you verify and then you validate. I'm going to be pushing back on this this prescription, and I think that you know, I don't think that this prescription is something that we should be enforcing. But I think, just to sort of give it its credit, you can sort of see why this might be a compelling source of concern if you start to think about some of the sort of difficulties that arise, particularly in these, you know, highly complex simulations. You know, it can often be very difficult because of the, you know, complexities and nonlinearities in the code to sort of distinguish between, you know, what is the effect of a numerical error and what's sort of the genuine product of the underlying sort of conceptual equations, and what might be sort of a novel phenomenon that we didn't realize was the implication of the underlying conceptual equations. So I'll talk a little bit about why this might make a little bit more sense, well, sort of towards the end, but I just wanted to sort of say that. Now, that's a sort of epistemic prescription that's advanced. Eric Winsberg has argued that, like, descriptively, for highly complex simulations, verification and validation can't be separated. And, you know, the reason for this, I could go and talk about this for a long time, and I don't really have time to, but, like, for example, the standard way to verify a simulation would be benchmarking it against a known analytic solution. So you set up put the initial conditions into the simulation, you evolve it and see if it matches up with your analytic expectations. The numerical output matches up with your analytic expectations. But, you know, remember that the whole point of introducing simulation was precisely in those cases where we don't typically have analytic solutions for anything, you know, any of the sort of more realistic scenarios that we might, you know, want to look at. And so what this ends up doing is it means that it's very difficult to you know, confidently say that we've verified or eliminated sources of numerical error for these highly complex simulations when we can only sort of test very simple cases. The question then is whether or not this sort of disparity poses a fatal epistemic problem for complex simulations. And, you know, again, to presage my conclusion, I don't think it does. But so here's the sort of broad outline of the talk. So the broad question, how can simulations be epistemically justified, as I've just sort of tried to explain, has led to this question of, you know, whether or not this problem of error cancellation is something that needs some particularly strong prescriptions about how we proceed with verification and validation. And then to what I'm going to do now is I'm going to ask following this discussion of the outline of the talk, what I'd like to do is I'd like to ask, you know, what epistemic function are the things that are often called verification tests actually serving? And the sort of spoiler alert is that I don't think that they're just checking for numerical error, as the sort of name verification sort of suggests. They serve, I think, as important probes into the space of simulation models, and sort of to increase our knowledge of the way that, you know, the different kinds of simulation models might work, and, you know, what their strengths and weaknesses are, things like that. And in particular, the way that I'm going to do that is by you know, looking at a particular case study of the development of tests for fluid mixing instabilities in MHD galaxy simulations. And on the basis of that, sort of this talk has a sort of quasi-nested structure. We'll come back and try to give a brief answer to the question of whether or not this separation prescription is really necessary. And in particular, I don't think it's as compelling once we see what verification tests can actually do for us epistemically. Now, this is a bit of a deep dive talk, and then we're not going to come all the way up for here because I don't have time for that. But hopefully, you know, you can see how the answers on the right-hand side of the screen might lead to a kind of sketch of an answer to the top question of whether or not, you know, how simulations in general can be epistemically justified, even if I think this, you know, I admit that this is more of a case study, and I don't intend for this to be a comprehensive answer to that top question in this talk. So, how are we doing on time? Okay. Why isn't it going? Okay. So, verification tests. What are they? Well, again, I'm imagining most of you sort of have some sense, but what I'm talking about is just you have a set of initial conditions, you run the simulation on those initial conditions, and typically you compare it to something like a known analytic solution or some other benchmark. And then disparities between the simulation output and the expected result then are supposed to suggest a numerical deficiency within the code. They're pretty ubiquitous in method papers. As part of this project, I did a survey of sort of representative MHD codes and the various tests that were reported in those method papers, just as sort of a very simple example of one. Like the Sedov-Taylor point explosion is where you have, it's a 2D scenario typically, and you set it up with a constant density everywhere, and then you spike the density in the middle and then let it evolve. And because this is a nice symmetrical situation, there's a known analytic solution for what's going to happen, and so you can compare the way that the numerical code handles this to the sort of known analytic solution and check whether or not there are any significant disparities. That would be a very simple example of a verification test. Now, again, the question is, what function do these epistemic function do these verification tests serve? And my conclusion is going to be that they serve a much wider function than just this sort of simple checking for numerical error. And in particular, what I'm going to do is I'm going to investigate a case study of sort of fluid mixing instability tests. These are the Kelvin-Helmholtz and Raleigh-Taylor tests that I have listed here. You'll notice actually that these tests didn't really make it onto the scene until around 2008, and that's not a coincidence. That's part of the narrative here. In particular, these tests didn't really make appearances in method papers until codes were, reasonably able to handle the phenomenon in question. So fluid mixing instabilities are sort of mixing phenomena that are found at the sort of interface between two fluids with different densities and relative speeds. You have Kelvin-Helmholtz, which happens when the velocities are shear, and then Raleigh-Taylor, which happens when the relative velocities are perpendicular. Now, in the sort of context of these MHD codes, there was a code comparison project published in 2007. Essentially, I'm going to be doing a bunch of hand waving here, I'm afraid, that essentially showing that a particular subtype of simulation, namely these what are so-called smooth particle hydrodynamic methods, tended to suppress these kinds of instabilities and thus suppress the mixing of fluids relative to Eulerian grid methods, which on the one hand, SPH methods are Lagrangian methods. On the other hand, the grid-based methods are Eulerian methods. Apologies. They developed essentially this, what's sort of colloquially come to be called in the literature the blob test, which is you put a spherical cloud of gas inside a supersonic wind tunnel with the expectation that a bow shock is going to form and then dissipate via these instabilities. And then the rate of dissipation can be sort of compared with theoretical expectations of the expected rate of these dissipations. Now, the thing to note here is just that, this particular paper, this particular code comparison kicked off a sort of flurry of activity in the literature aimed at diagnosing the problem with these SPH methods. Some suggested that the problem had to do with insufficient mixing of particles at sort of subgrid scales. Others diagnosed it as the problem as a kind of artificial surface tension that was a result of the discretization of the SPH equations. Various other people came up with sort of alternative tests of these fluid mixing instability issues. In particular, they did so on the grounds that at least the argument was that the Egert's blob test sort of gave a sort of distorted picture of the undermixing problem that as it actually occurred in the SPH methods. So Robertson and McNally both advanced sort of alternative, and ultimately this led to the development of new simulation methods that tried various targeted approaches to dealing with this undermixing problem in SPH method. Just as a sort of example, I think Hopkins, the main thing is that instead of sort of deriving the density, the pressure from a sort of discontinuous density, they they calculated it directly. And in particular, this has actually marked a pretty significant shift in the simulation literature. The simulation methods before 2007 are so-called traditional SPH, and then afterwards we have sort of called modern SPH. And the important thing here for my purposes is that these problems were not discussed in sort of purely numerical terms. And by this, I don't mean that the various tests were sort of phrased in terms of physical initial conditions. Obviously, that could just be a matter of convenience. What I mean is that the goal here is specifically to understand how these code types handle the modeling of specific physical phenomena, and the various attempts to elucidate the problem and develop, and then and make various attempts to elucidate this problem and develop solutions. Sometimes with respect to sort of physical fictions that are introduced into the simulation. So one of the solutions to the undermixing problem was to introduce, for example, an artificial thermal conductivity term. And these are not just sort of incidental goals to checking the numerics in question. How am I doing on time? Good. Okay. And importantly, so the takeaway here is that these verification tests are not sort of always obvious or canonical in the way that you might expect if they were just checking for numerical error. The goal here, they're not just sort of new and improved ways of checking for numerical fidelity. They serve as sort of probes at the space of simulation code types. So from the thread of the MHD simulation literature, we now have tests that check for the ability of simulation to handle these fluid mixing instabilities. But we also have a better understanding overall of the strengths and weaknesses of SPH methods versus, relative to grid-based methods. And this wouldn't have happened if we had sort of restricted ourselves to like purely numerical methods up front, as the sort of strict V and V separation prescription suggests. Ultimately, I should stress, we even got, we have better models now as a result of this sort of trajectory. Now, isn't it? Okay. I sort of already said that. Sorry. So the answer to the question that I sort of presented as sort of at the lowest level of this talk, which is, what epistemic function do these verification tests serve? Well, I'd like to make the case that, verification tests aren't just used to check for numerical error. They're serving as these important probes to the space of simulation models as well. They're giving us knowledge about the different sort of possibilities for simulation modeling. So with that sort of established, let's take one step back up. Now recall that our sort of second order question was, does this problem of error cancellation require a separation of verification and validation, per the strict account? Now that I have this sort of example of verification tests in hand, what I want to do is ask, why was this cancellation of errors problem particularly concerning? And in particular, we'll start by asking this from the sort of strict V and V perspective. Now, if we think about it in our scientific theorizing, we always run the risk of making errors and being radically wrong. That's just the problem of underdetermination. There's nothing particularly special there. We generally regard that risk as feasible because we expect, a rigorous search of the inductive space will eventually reveal where we went wrong. We don't think, for example, that the phenomena are conspiring to subvert our theorizing or something like that. And so if we are to regard the problem of error cancellation as regarding, warranting this extra prescription of caution in separating verification and validation, then I think it needs to be on the basis of some additional concern over and above the sort of regular underdetermination worry that we sort of hold the rest of science to.
Kevin, there are two kinds of verification problems. One is the relationship between reality and conceptual model, and the other between conceptual model and the computer model, right? In the circle.
So verification concerns the verification concerns the relationship between the conceptual model and the computerized model, so the theoretical equations and the simulation code. Validation concerns the relationship between the code and the reality, and there's various words that are used to describe the overall relationship.
But there's also the relationship between reality and the conceptual model, which
yes, that's the goal.
Is labeled as a form of verification.
Some people do talk about the way that I'm using the term here is that's a little. I'm not using the term in that way. I'm sure that people use the term colloquially to mean that.
Okay. So you only are comparing the relationship between the conceptual model and the computer model, and the relationship between the conceptual model and reality. That's the verification validation contract.
No, verification deals with the one half of, so there's the bridge, computer model and the computer code. Sorry. When you say computer model, sorry, I think I mixed up. I misheard you. So there's the conceptual model, the theoretical equation, and the simulation code. That relationship it has to do with verification. There's the simulation code and the real world. That's validation, and then the bridge between the bridge that they form, you might between hopefully forms a correspondence between the conceptual model and the real world. That's called sometimes, as I said, the word validation is used in contradictory ways. Sometimes that's called validation. Sometimes that's called qualification. There's a bunch of words for it, but like that's the goal, ultimately. Right. Clear. Okay. All right. Sorry, where was I? So the strict V&V answer as to why this cancellation of errors problem is particularly concerning has to do with, again, the opacity of the simulation plus the sparseness of the data now. It essentially makes the risk of error much more systematic. Let's see, and I want to suggest that this answer does, I think, make a little bit of sense if we were to regard verification tests as just checking for numerical fidelity. In that case, we'd have no reason to believe that we have a way to sort of rigorously search for weaknesses in our simulation model. But as I've tried to argue, simulationists aren't limited to a set of predefined tools. By developing these sort of newer tests, we're not just sort of creating new mechanisms for testing numerical fidelity. Of course, that's going on. But we're probing the space of simulation models and sort of developing progressively better models. And while it's true, we'll probably never get to the point where it can be sort of top-down, absolutely certain that everything is in perfect shape. That I regard that risk that is sort of the same way we can never be absolutely certain, from the top down, that our scientific theory, rigorously describes the whole world. Like there's always the possibility that something might come in and show that we're wrong. So the question, does this threat of error cancellation require strict separation between verification and validation? I don't think so. I think that if we understand what verification tests are doing for us, not just numerically, but in the sense of probing the space of simulations, we can regard this as a kind of rigorous attempt, as a set of tools that we can use to rigorously search for errors in ways that, undercut this particular, the gravity of the concern that the strict V&V prescription proponents make. That's not to again, I don't want to stress that that's not to dismiss the reality of the worry of error cancellation. Obviously, on some level, that's always going to be a source of concern. But I do think that it sort of mitigates, it decreases the level of credence that we should give to that notion that this is some sort of overwhelming problem that requires this very strict separation between verification and validation in the way they suggest. And so hopefully, just to sort of go through what I started out with the question of how can simulations be epistemically justified? And that sort of gave rise to this particular debate within the sort of verification and validation literature about whether or not this particular threat of error cancellation is severe enough to warrant the separation between verification and validation, a separation between the sort of strictly numeric, the strict numerics and the physical side of simulation justification. That leads to the sort of question of what function do these allegedly verification tests serve? And again, I want to sort of stress that the name verification, now that I've made my case, is perhaps a little misleading. Verification, insofar as it means strictly numerical, suggests that these things are purely numerical, and I don't think they're purely numerical. I gave you this sort of test study with the fluid mixing instability, case study with the fluid mixing instabilities, which suggests that there's a lot more going on epistemically with verification tests, and to regard them as simply tests of numerical error would be, I think, to deny us very, very important epistemic leverage points that can be used to progressively develop better models. And then finally, sort of taking that conclusion one step up, if we can probe the space of simulation models, then I think that this threat of error cancellation is defeasible in ways that I think that the proponents of the strict V&V prescription would reject. Now, of course, I'm not going to be able to get to the question of generally how simulations can be epistemically justified. That's sort of a later project, but hopefully that sort of gives you this particular case study gives you a sketch of how a positive account might be constructed, that sort of could stand as a sort of an alternative to the sort of strict B&B account. All right, and thank you very much.
So, Kevin, I have a very general question for you. This is something that Klaus Weisbart and I had several conversations about several years ago, and he never really satisfactorily convinced me. So maybe you can. I honestly don't see any real epistemic difference between simulations and traditional pencil and paper calculations. So let me explain what I mean. So if you're a physicist and you're doing, let's say, lattice QCD, and you're really good at calculations, you set up your conceptual model exactly the way you're describing, figure out your calculational algorithms, how you're actually going to compute your approximations and perturbations and do the discretization, and you do error analysis, but you just do it all pencil and paper. And what's the epistemic difference between that and simulation? And the only possible thing the only thing I can think of is what you refer to as the opacity of the simulation. But again, think about Navier doing the logarithm tables. He didn't do all the calculations himself. He farmed out most of the work to drudges. And we can imagine that Navier didn't have a really good grip on all the calculational tricks that all these systems were using. And so it was in some sense just as opaque to him as the computer simulation is to us. In principle, of course, he could have figured it out. Presumably, he actually knew. But this is I'm telling a motivational story. And in principle, of course, these computer simulations are far beyond the cognitive capacity of any real human being. But I don't see any in principle difference here. We could, given enough brain power, given enough time, presumably in principle, in some sense, we could figure it out. So what is epistemically different about simulations and just traditional pencil and paper calculations?
That's a good question. And I'm not sure I'm going to give you a totally satisfactory answer, but I do think that your intuitions are channeling along the right lines. So the main thing I'd suggest is that it sort of depends a little bit on whether or not what we have here is a situation. I'm not super familiar with QCD, so you'll forgive me, or lattice QCD, but if what we have here are, if we can regard it as like a set of equations that are sort of taken to stand in for sort of deeper, more sort of explanation-oriented conceptual equations or something like that. If that's the case, then possibly, yeah, there is something like what the model that I'm going on here, insofar as there's this, intermediary between what we take to be our sort of conceptual understanding of the thing and the thing itself. If it's those equations, if that's not what's going on, then it might be the case that there's a certainly always in science it's the case that we have to be concerned about, like, what effects are numerical our sort of idealization, what kind of effects are our idealizations introducing? Are they introducing things that are not going to ruin the faithfulness of our equations to the of our theory to the phenomena? I think that the thing that's different about the simulation is precisely that there's this sort of intermediate step. And insofar as you could characterize a non-computational situation as having that intermediate step, you could potentially run a similar kind of argument. And there's, I'd say you're right. But I'd have to think a little bit more about whether or not there aren't the other situations that, sort of go beyond that might be amenable to this kind of analysis. But I'm not opposed to that, I guess.
Just to add to that, I just grabbed lattice QCD. It just popped to mind for some reason. I think that the situation I'm describing is endemic to all of physics. You don't have to get so fancy pants as lattice QCD. Think about stability analysis of the solar system. where you do first order, second order, third order approximations, and in the 19th century they were all doing this with pencil and paper, and they managed to work out that second order everything's stable, third order you get chaos, and he was using calculational algorithms to do this stuff, and again, I think this happens whenever you're doing perturbative analysis. You are faced with, as far as I can see, exactly the same kind of formal conceptual structure of your Sargent circle.
Yeah,
So,
I mean, insofar, yeah, I think you're broadly, like, you're correct, certainly, that perturbation analysis as like a kind of, they're not discretized in quite the way that they are in a computer simulation, but yeah, well, in some cases I think they actually are like that. But yeah, they serve as a kind of intermediary for the underlying analytic equations that we, Newton's laws that we take to be our conceptual, like our sort of true conceptual understanding of what's going on. So yes, that problem, in that sense, yeah, it'd be pretty ubiquitous. I think that there are some cases where, like, where the equations are sort of numerically tractable, where this concern is just sort of ignored because we don't, like, the numerics are not as complicated as they are in galaxy simulations, so we can just sort of brush it off and it's not as much a concern. But yeah, I think your argument that this is a little more of a ubiquitous thing in general is probably, I think that's a line that could be followed. Yeah, I'd have to think.
I will say in your favor that I think the problems that you're pointing to come out with really with great clarity in the kinds of case studies you're looking at. So I think that this work is valuable if only for that reason. But I think it's probably but I don't think only for that reason.
Fair enough. Thank you.
I had a question.
Yeah, go ahead.
In the Sargent circle, there's a kind of analytic separation between these different relationships between the three circles. Okay, the three: reality, conceptual model, and computerized model. When I was just looking around at pictures of the Sargent circle, sometimes it's represented as different forms of verification in each of the chords that separate those. So
yeah, this has been part of the this has been part of the issue with trying to study this stuff, is that different fields will use different terms in
but
distinct ways.
in a real simulation, what you are actually often faced with is an amalgamation of analytic models, conceptual models, approximations, and data, right? I mean, there's actually all of these things are involved in the comparison of the computer model and the reality model simultaneously. And if I've understood correctly, the purpose of this kind of circle is to say, if we imagine prying these apart into different relationships, we would have something like this. But it's not a claim that, in fact, in a real simulation, in any domain of physics that I know, you would actually only have conceptual models, or only have computer models, or only have heuristics, or only have analytical models digitized and appropriately approximated. Is that the case? Is it the case that in a real simulation that is being done in astrophysics or particle physics, these things are amalgamated in different ways, but we're trying to get analytic purchase on this by separating them? Is that?
In some regards, yes. And part of the reason why I was interested in physics for this is precisely because, for the most part, physicists don't talk in this way. This is something that came up in the sort of philosophy literature, because but didn't reflect the sort of terminological ways that physicists were talking. And as I've tried to suggest, part of the project was to try to get a handle on what they were doing and whether or not it ran afoul of these prescriptions that sort of come out. I should say that this doesn't come purely from the philosophy. It was imported from, like, again, engineering, like various fields in engineering. And so there are fields that do try to separate these things out in practice very clean, as cleanly as possible. They obviously acknowledge that certain concessions must be made to practicality, of course, but there really is an effort in some fields to try to make this like reflective of actual practice rather than just this sort of purely analytical framework for understanding, what's going on conceptually, which is what I think the philosophers typically were sort of taking it as a picture of. So, but yes, and in physics, I think a lot of this stuff gets amalgamated, and the question then becomes whether or not, to what extent is this amalgamation just a sort of practical necessity, or is it sort of go core to the principle of like how this stuff is epistemically justified? And what I take some of Windward's arguments to show, and what I'd like to sort of provide an alternative to is precisely something like, this amalgamation isn't always just a sort of practical necessity. It makes sense epistemically to try to do some of these, some of these things at the same time, as it were. Even if the jargon is often useful for, I think the jargon is in fact useful for analytically separating out some of this stuff when the occasion demands.
Jamie?
Yeah, I mean, one thing I was going to say is just to push back on Eric a little bit, and but I think we sort of got there in the end, and thinking that it's unclear to me that you need for simulations to be distinctive in principle from other sort of more generic cases of calculations in order for there to be something epistemically interesting about simulations. Might just be that, as you sort of got to, there's this is sort of a different kind of practice where you see scientists doing something a little bit different in terms of how they go about doing what we're calling here validation and verification. And so in some ways it's actually seems to me to be a virtue if this turns out to be a more generic thing, because then you can use one perhaps sort of more extreme case of how this works, and then reflect back upon other kinds of theoretical calculations that don't involve this, maybe as this sort of separation in the same kind of way, and think about whether it generalizes, whether there's, and thinking about connections rather than difference, and that doesn't seem to be a problem for the interest of what's going on here. But I think that's maybe kind of where we ended up. So
yeah. No, absolutely. I think something I didn't mention was, I mean, like part of my goal here, again, the thrust of my argument against the V&V prescription is say, look, you're holding simulations to a standard that we don't hold regular science, like regular sort of experimental science to. And so absolutely, my goal here is to, at least in some regards, suggest that simulations are not all that different from sort of ordinary scientific. I do think, there's some interesting parallels to be drawn as well in the sort of the extension of this work. I've drawn on some of the work by Isabelle Pichard, I believe, who like pointing out the interesting ways that experiments are used in ways that are sort of not as straightforward as one might think, that sort of look a little bit more like this. They're highlighting the ways in which experiments can be used in a kind of exploratory way, and that in those cases, I think those look a little bit more like the simulation story that I'm trying to tell here. So I'm definitely amenable to drawing interesting parallels in that regard.
Yeah. I'll let Priya go first, but I'll re-raise my hand.
Oh, she waited for me. Okay. So I think there's something I find sort of problematic right here, and that is that shouldn't inference be somewhere here? And that's the way in which simulations are different from replicable, experiments, manipulable experiments, right? So these are controlled experiments that you can do in the laboratory. Simulations permit a very different kind of inference because there's a longer chain that is needed often. So in this Sargent diagram, I'm a little uncomfortable because to me, it seems like inference has to be, the ability to infer and the robustness of inference has to somehow be, for vectors here, has to be something here. And seems like a very incomplete kind of breakdown. I understand the utility of it, and I can see, as you said, that, it's adapted from engineering, but people are really trying to cleanly separate out these subsystems, if you will. But, yeah, I don't know, what do you think, Peter? I mean, there's something, right? I mean, inference should be here somewhere.
Yeah, so I think that the key here is to not try. I wouldn't regard these arrows as arrows of inference per se. They're the goal is to get to have the arrows represent kind of correspondences, and then on the basis of these correspondences, we can then make inferences about in various there might be various techniques we use to try to infer that these correspondences are there or within the appropriate regimes or whatever. And then on the basis of these correspondences, we can then infer, again, hopefully that like now we understand this thing about how galaxies form that we didn't understand previously. Like one of the things that came out of getting better handle on, for example, fluid mixing instabilities and having these new traditional, new modern SPH methods that can handle these sort of complicated mixing is that, we found out that, what was the exact, it was something to do with like how these fluid mixing instabilities are really important for, how much gas gets stripped off of these galaxies under, certain conditions or something like that. Like, that's the inference that I'm interested in. The arrows here aren't exactly inferences. So far, that's not primarily what I'm interested in terms of like, setting up the structure of inference, the role that this stuff plays in the network of inferences that you might want to make about in the scientific project.
Jamie?
Yeah, so I thought your case study was really interesting, but because I don't know anything about it, it'd be really helpful for me if you could maybe say again what about the case study, just re-describe the features of the case study that you think lead to this new understanding of what's going on in verification as this kind of, it's mixing verification and validation in some sense, and it's allowing you to sort of probe the space of the simulations. And that just went by a little fast for me, so it'd be great to just get a better handle on what's going on there.
Yeah, sure. So yeah, basically the insight, the sort of the contention of Egert's was just that, look, SPH methods relative to these Eulerian grid methods undermix. And of course, then the question is like, is it really obviously there is some amount of mixing that actually happens in the real world. And so now we need to figure out, is SPH really undermixing? And the reason why I sort of phrase it that way is because ultimately that's the conclusion they came to. Or perhaps are the Eulerian grid methods overmixing? And again, the goal here is just to point out that like these tests weren't sort of obvious or canonical. Part of the process was investigations into the structure of SPH, like the SPH models, relative to the kinds of discretizations and idealizations that the grid-based methods had to use. They use different idealizations, they use different principles, and then the output of this was like a new suite of models that sort of again tried to correct for these in various ways. And in particular, the thing that I was just stressing is that I didn't really stress that might be a little bit helpful here is that the kind of discussion that we get out of this, like the kind of we're able to from conversations like this, we are able to sort of peg our confidence in the ability of our simulations to simulate certain phenomena, like to simulate the galaxies, for instance, in this case, relative to various phenomena that we're confident that our simulation is able to handle. So we think that this simulations post 2008 are reasonably able to handle fluid mixing instabilities, and therefore we're able to make inferences about phenomena that are dependent on these fluid mixing instabilities that don't on the basis of these simulations. That's different from the sort of especially if you look at some of the purely numerical verification techniques that are often sort of advanced in the verification and validation literature, where like they're concerned with like round off error generally. Or like, but just having an analysis of round off error in general isn't particularly helpful if you're trying to make inferences about physical, like when is my simulation adequate to certain kinds of physical phenomena. There's just sort of categorically, it's difficult to sort of pick those out. I'm not saying it can't be done, like, obviously, but this kind of analysis is like by specifically sort of targeting physical phenomena makes, targets the development of these simulations along the lines of elucidating these phenomena. And, I think that by doing that, we get, better models which allow for, other disparities to come out. And, it's sort of a progressive sort of epistemic circle in that sense that, we can progressively refine models once we, in that way.
Great, thank you.
Any more questions?
I think we've covered him enough, right?
Yeah.
Questions.
Yeah.
Thank you very much,
Fun.
Kevin.
That was great, very interesting, yeah.
Yeah.
Yeah, thank you all. I appreciate it.
Yeah, so Jamie, do you want to close?
Yeah, so I guess I'll just repeat again, thank you, Kevin. That was a really wonderful talk. And I think we're moving into colloquium now, so I'll close the meeting and see most of you next time.
Take care, folks.
Bye.